All right, so let's get right into it. You see this stuff all the time, right? A news report, a study, a poll, and they all claim to know what an entire country is thinking or doing. But how? I mean, how on earth can they possibly know that? It just sounds impossible, doesn't it? How can this tiny little handful of people speak for the whole nation? It really does feel like some kind of magic trick. But here's the cool part. It's not magic at all. It's this powerful idea called statistical inference, and today we're going to pull back that curtain and show you exactly how the trick works. And believe it or not, the whole thing starts with something super simple: soup. Seriously, think about it. If you make a giant pot of soup, you don't have to eat the whole thing to know what it tastes like, right? You just need one well-stirred spoonful. And that simple idea, well, that's the key to everything. So, first up, we have what's called the population. In our analogy, that's easy. It's the entire pot of soup. It's the whole group we're curious about. For the example we're going to run with, our population is every single person in England who has eaten a meal at a restaurant. Now, obviously, asking everyone would be a massive, incredibly expensive job. That's a census. So instead, just like with the soup, we take a sample. This is our spoonful. We just ask a small, randomly selected group, in this case, 1,101 people, what they paid for their last meal out. So what does our spoonful taste like? Well, that's our statistic. It's a number that describes the sample we just took. For our group of 101 people, we crunched the numbers and bam, the average cost for a meal was $66.10. This is a real, concrete number that we actually observed. But here's the thing. That £66.10 isn't the real prize. What we're really hunting for is the parameter. In our soup world, this is the true taste of the entire pot. It's the actual average meal cost for everyone in England. This is the big mystery number we're trying to uncover. We can't measure it directly, but our little statistic, it's the crucial clue that helps us make a really educated guess. Okay, but this is where it gets a little tricky, right? Here's the crucial question. What if our spoonful, our one sample, just happened to be a bit unusual? What if by pure random chance we happen to pick people who ate at slightly fancier or maybe slightly cheaper restaurants than average? I mean, what if we took a totally different spoonful? A second random sample might give us an average of 67.81, while another one could come out to 65.29. Now, this isn't a mistake. It's a completely natural and expected thing called sampling variability. Every random sample is going to be a little bit different. So, if every sample is going to be a little different, how can we ever feel confident in our result? How do we get past all that randomness? Well, this is where statisticians came up with a really brilliant thought experiment. We can't actually go out and take thousands of samples in the real world, but we can imagine what would happen if we did. So here's how the thought experiment goes. Imagine taking one random sample and calculating its average. You write it down. Then you do it again and again and again, thousands of times. You'd end up with this massive list of all these different sample averages. So what happens when you plot every single one of them on a chart? You'd probably expect total chaos, right? Just a random mess of numbers. But what actually happens is amazing. Out of all that randomness, a beautiful, predictable pattern emerges. The distribution of all those sample averages forms a perfect bell curve, also known as a normal distribution. This is no coincidence. It's a fundamental law of statistics called the Central Limit Theorem. This bell curve is so powerful because it tells us three incredibly important things. First, most of our sample averages are going to cluster right around the true unknown population average. Second, if you took the average of all of our thousands of samples, you would land on the exact true population average. And third, and this is key, we can actually measure how spread out these samples are. And that measure of spread has a special name, the standard error. Think of it as the typical amount of error we can expect from any single sample, just due to random chance. So a smaller standard error is a great thing. It means our samples are all packed tightly together, and that gives us a much more precise estimate. Okay, let's just quickly clear something up here because this trips up a lot of people. Standard deviation is different from standard error. Standard deviation tells you how spread out the data is inside your one sample. It just describes what you have. But standard error is about inference. It estimates the spread you'd expect to see if you took tons of different samples. It's all about measuring the precision of your guess for the whole population. All right, let's bring this all together. We know our single sample won't be perfect, But we also know that most samples tend to land pretty close to the true value, and we've got the standard error to measure that typical spread. So with this toolkit, we can stop making just one single guess, and we can start building a range of plausible values. So remember our single statistic? Our sample gave us an average meal cost of £66 and 10 pence. This is our best single guess, what's called a point estimate. But we know it's probably not exactly right. So instead of just using that one number, we use the standard error to build a range, kind of a safety net around it. So now we can say something much more powerful. We are 95% confident that the true average meal cost for everyone in England falls somewhere between $60.35 and $71.85. This range is our confidence interval. But what does 95% confident really mean? It's a common mistake to think there's a 95% chance the true average is in our range. The true average is a fixed number. It's either in our range or it isn't. Our confidence is in the method. It means if we were to repeat this whole process 100 times with 100 different samples, the method we used would produce a range that successfully captures the true average 95 out of those 100 times. Now, 95% sounds pretty good. But what if that's not enough? What if you're dealing with something super critical and you want to be, say, 99% sure that your range contains the true value? Can we do that? Yep, we sure can. But there's a trade-off. To be more confident, you have to cast a wider net. A 99% confidence interval is much wider, stretching from about 58 pounds all the way to 74 pounds. You're more certain you've captured the true value, but your estimate has become less precise. On the flip side, a 90% confidence interval gives you a tighter, more precise estimate, but you do so with a little less certainty. It's this constant dance between confidence and precision. Ultimately, it all comes down to this. This quote really just sums up the entire process perfectly. We start with a small, manageable piece of information, our sample statistic, and we use the predictable laws of probability to make a confident, reasoned statement about a much bigger, unknown truth, the population parameter. So the next time you see a poll or a study, you'll know the incredible thought process that's happening behind it. You'll know that a small, random sample can tell a powerful story about the whole population, not through magic, but through the predictable laws of probability. And now you have the tools to ask the right questions. So what makes a statistic trustworthy to you? Is it a larger sample size that shrinks that standard error? Or is it a high confidence level that gives you a wider but safer bet?